really a great pleasure and honor to have today's speaker, Professor Yifan Cheng. It's unusual for me. I will take a little longer time to introduce Professor Cheng for the audience, both because of the very unique background of him and our personal relationships. I always, in my own career, I always feel that for biology, when physicists get interested in biology, something very interesting will happen. For a physicist who really understands biology, gets interested in biology, something wonderful, almost for sure will happen. We all know modern cell biology, in a way, was initiated by EM microscopist, George Prady, right? Without him, cell biology wouldn't be here. What I believe that I can very confidently say, what Yifan has been doing is bring another revolution to modern biology. Okay, this is what Cryo-EM that Yifan is doing. But before I go into this, I wanted to say that Yifan has always been extremely passionate on the EM of solving biological questions. And he has been very persistently of pursuing this in a way like he's pursuing his marathon running. So for people who know that, he has just ran the number 6 marathon this year alone. Just finished one in Beijing. Right. Now for students, I want to say things. For students who took my course on the biophysics of protein structure, so I always say that one day it would be a dream if we have a super camera can take snapshots of molecules. Then we would be able to answer, numerous questions otherwise we wouldn't be able to do. So to me, I always say it's a dream. But I never tell students that I thought that this dream would be almost impossible, right? But for Yifan, impossible is nothing, right? He made it happen. We now can literally take pictures of individual molecules and then convert them into atomic structures and tell people that how very complicated molecules, how do they move? Now for physicists, you think that that's easy, that's EM can do. But biological molecules, they are not as tamed as most of the physicists would think, because they have extremely so-called moving behaviors, complications, and so on and so forth. For example, if you bombard with electron beams, they move, right? You have extremely low signals. So when you take pictures, you can hardly see the signals of the molecule over the background. So these are some of the things that most of the people a few years ago think that these are probably not possible to be overcome because these are inherently issues of the molecules in biology. But Yifan took a different approach. He was able to say that if sensitivity is not enough, let's use physics methods. Can we find better ones? Rather than conventional cameras using CMOS, he said, let's count electrons. Right? If molecule moves, I tag them. In other words, like a clock. If you know it's 1 minute slow or 1 minute fast, if you recalibrate them. But of course, tagging molecules is incredibly difficult. So among many other things, what Yifan has done make Cryo-EM to be the stage now. It's extremely important revolution to molecular cell biology, to biology as a whole, because now we are able to view molecules in their physiological states. Now, these are things that means a lot to biologists, meaning that many of the molecules, they do not have a simple state. They have a mixture of many states because this is what they are needed to perform biological functions. And now we are able to see them. And this is what Yifan's wonderful contributions. So Yifan was trained as a physicist graduated from Wuhan University, got a PhD degree from Institute of Physics in Chinese Academy of Science. Then he worked with several of the leading EM people in the field over the many years. Right? After his last stop in Harvard as a research associate, so he was recruited to UCSF, and within very short time, he has risen to his current status. I'm not going to take any more time of Yifan. Let's hear what Yifan is going to tell us the exciting landscape of Cryo-EM.
Thank you.
Let's welcome Yifan.
Thank you, Min-jae, for your very generous kind introduction. And also, I want to thank Min-jae and then also for the others for the opportunity to speak here. And actually was here in Hong Kong last year. We had an Cryo-EM Golden Conference in Hong Kong last summer, and at that time I didn't have the opportunity to visit this campus. It was wonderful to be here. So today I'm going to talk to you mostly about the single particle Cryo-EM, and I was using a title called Revolution in Structural Biology. In a way, it is indeed revolutionized structural biology. So. I just started with this slide that a few years ago, that back in 2014, that's almost 3 years ago, Werner Kuplan wrote a review or feature article for Science. And he gave a title called Resolution Revolution, because at that time it was really marked the beginning of this new era, that a number of structures that reached the atomic resolution, which has been resistant for the traditional crystallography approach, particularly in the trip channel that we worked on. And this is a ribosome, and this is another large complex that Werner Kuplan worked on. And a year later, and then there was also another feature article in the Nature that in the background, this is actually the TRPV1 structure we did, and with this famous sort of feast to demonstrating that a new upcoming, which means the Cryo-EM, against the establishment. That's like the crystallography, traditional crystallography. They used the title that a revolution will not be crystallized. Since then, people started thinking about Cryo-EM really changed the structural biology, and then it became really a revolution in the field. And it was very exciting for us. And until now, that it's very clear now that single particle EM is actually already became the method of choice. It's not only say one of them, but really the method of choice for studying many macromolecule complex that are resistant to crystallography for many years. And this is really the current state, and it's full of excitement. And then probably everywhere you go, and then if you look at the Nature, almost every few issues, you get a number of structures by Cryo-EM, which I feel extremely lucky that actually experienced this whole thing. And since the early time. So for that, I want to take a step back and then I'll give you some brief background about what EM is about. So in electron microscopy, basically we're taking images of a three-dimensional object. They're just like a projection, like you have on the screen. That basically it's a EM picture is basically a two-dimensional projection of a three-dimensional object. And this cartoon is actually a little bit misleading because this shows a shadow. In actual image, it's not a shadow, but a real projection, just like a chest X-ray picture, right? Carries all the information through that. And so and what this shows is that what you see a two-dimensional projection does not really mean that how the 3D looks like. And so the whole idea is that how do you reconstruct this three-dimensional object from 2D projection images? Mathematically, this has been very well established. This is called the central section theorem. The idea is that if you have a three-dimensional object, and you have any direction, you have a two-dimensional projection of this three-dimensional object. And if you do a Fourier transform of this three-dimensional, these 2D projection images, what you obtain is a Fourier transform, a central section Fourier transform of a 3D Fourier transform directly from here. So in a way that if you have many different views of the same 3D object in different view, that you know the relative orientation between them, you can reconstruct the whole thing in Fourier space with both amplitude and phase. Then a reverse Fourier transform will give you the structure. This is the basic idea that David Rose and Alan Crook used in 1968 to reconstruct a three-dimensional object from 2D micrograph. And Alan Crook later got the Nobel Prize for partly because of this work, that his pioneer work for that. Now, EM is actually initially was developed for actually to try to observe the biologic sample. But if you compare EM and X-ray, the difference is that EM electron scatter is much stronger than X-ray. It's almost 1,000-fold stronger than X-ray. Therefore, you can take a chest X-ray picture, but you cannot do this with EM, with the electron, because the electron cannot travel too far in the air. The scatter is too strong. For electron to travel distance, one have to put them in the vacuum. That's why electron microscope always we have to deal with vacuum. Now, therefore, you have to put a biologic sample into the vacuum. The one problem with any biologic sample put into the vacuum is the dehydration. Any biologic sample put in the vacuum, the first thing happens is dehydration, water being sucked out, everything collapses since being destroyed. So and this is the dehydration, the issue that is making a major limitation for using electron microscope to observe any biologic sample. Now, for many years, the people developed many different ways to overcome this problem, and particularly in all kinds of staining and sample preparation, and particularly for cell biology. And it was very common to have a tissue sample or cellular sample that you use high pressure freeze them, then you substitute the water, remove all the water, and then you do plastic embedding and thin section and metal shuttling and all this kind of trick to finally getting a sample. And then if you open the textbook of like a cell, you see a lot of beautiful pictures. But that kind of sample preparation gives you a lot of information at the cellular level, but not at the atomic resolution level, because all the structural detail has been destroyed by sample preparation. Now, in order to overcome this dehydration problem and also the radiation damage problem, the first one demonstrated this one was Bob Glaser and his student, Ken Taylor. In 1974, they demonstrated that if you have a biologic sample, but what happens if you freeze them, and so that the water becomes solid, and then you can put them into the microscope, then you can maintain the hydration. And they demonstrate that by putting a catalyst crystal, frozen hydrated catalyst crystal, put in the microscope, and they can take a picture. At that time, they freeze the sample in liquid nitrogen. And then this cooling rate is not enough, so the ice, actually, the water frozen as a crystal. Therefore, this technique, in this way, they demonstrate that it is in principle that you can preserve biologic sample by doing the frozen hydration. And you can actually preserve biological information at the atomic resolution level because this crystal diffracts to almost 3 angstrom resolution. So therefore, the structural integrity is protected. However, to retrieve actually the structural information out of this type of image is still very challenging. Right? Around the same time, around 1970, middle 70, that there's another way to preserve biologic sample, to preserve the hydration, is to use sugar. So the idea is that you use sugar to substitute the water. And the sugar is very sticky, that in the microscope it will not be pumped out. So Nigel Unwin and Richard Henderson in 1975 was using this way to preserve a two-dimensional crystal membrane protein, particularly bacteriorhodopsin. And these are naturally formed two-dimensional crystal. And then from that kind of 2D crystal and prepared using the sugar embedding, from the crystal itself, they can get this kind of diffraction pattern. And from there, they can obtain the phase, the amplitude information. And then at the same time, they can take an image of this crystal. And a free transform of this image obtained give you both amplitude and phase information, more critical. And then combining these two, they were able to generate a projection images of a biological 2D crystal. And then to get in the 3D information, then they basically just tilt the specimen and obtain the 3D information. This was the bacteriorhodopsin structure. This was actually published in 1974. Was the first time showing any of the first transmembrane helices in any biologic sample transmembrane protein. Now this way has been actually later on. Richard spent a lot of years developing this technique and finally able to reach atomic resolution with the crystal. However, the limitation of this method is that you still need to form crystal. Can one deal with something without a crystal? If you cannot form crystal, what can you do? Right? Now, this was pioneered by Joachim Frank. Again, in 1975, he came up with this idea that if you imagine that if you form a crystal, what happens is that the crystal crystallization will align all the molecule into a precise orientation. And then so Joachim Frank saw that if you don't have a crystal, can you take an image and then computationally align them? to achieve the same thing that as crystallization does. So his idea is that if you can, using an averaging technique, that computationally align all the individual molecules, can you put them together? So he published this one as an idea back in the journal that most of the microscopists know. It's called ultramicroscopy. And this is the first volume. And Joachim said that at that time, probably they don't have anything to publish, so they are actually publishing an idea without actually real data. Actually took him 3 years later that they finally demonstrated that it was possible. This is an image of glutamine synthesis. And out of this individual image, you can see this is not a crystal. This is a negative stand EM. It's not a frozen hydration, but a negative stand. And computationally, they can average many particles and generate this kind of low resolution contour. But however, the resolution is still significantly higher than here. So this demonstrates that it is possible to use this computation approach to averaging things. This is now the so-called single particle EM. Right? The idea is that you average a lot of images of single molecules. Now, later on, that they, again, by tilting the specimen, they get a three-dimensional structure. Now, 10 years later, almost 1987, they did the first structure of ribosome. And this was without forming crystal. This is the first structure of ribosome, also at the low resolution level. Now, then, this is still a separate approach that is using a negative stand approach, but this is still the sample preparation itself has been limited to relatively low resolution. How to combine this one and frozen hydration together? This is a third work that by Jack Dubucher. He invented in 1984 a method to free as a frozen hydration, how to prepare individual sample of frozen hydration. They showed this beautiful image of a virus embedded in a thin layer of ice without any contrast enhancing reagent. So this is native conformation. And the method we are still using now after almost like 30, 40 years, right? So the method basically nowadays we're using a EM grease covered with this kind of commercially manufactured carbon film. In this carbon film, you can see that it's covered by this continuous carbon film with this regularly spaced hole. The diameter of this hole is about 1 to 2 micrometer. And then what we do is that we then put a droplet of your purified protein sample, and typically it's about 2 microliter or 1 to 2 microliter sample into this EM grease. Then you use a filter paper to blot most of 99% of the sample away and throw them in the garbage bin. And then remaining liquid, because of surface tension, will form a very thin liquid layer across these holes, and then holding them there. And then you rapidly plunge freeze this one into liquid ethane cooled by liquid nitrogen. This one is kept mostly at minus 200 degrees C, and then the cooling rate has to be about 100,000 degrees C per second. In such a high cooling rate, the liquid will frozen in its amorphous state without forming ice, without crystallizing. And if it crystallizing, it will destroy your sample. So in this way, what we end up is a thin layer of amorphous ice, which we call vitreous ice, with your protein sample embedded in it, and in all random orientation. Presumably, this sample are purified protein sample. They are in the same conformation. Then you put this one into electron microscope, and you take images of many different proteins. And each one is defined by 6 geometrical parameters. Basically, 3 defines spatial orientation, and 2 XY position, and 6 one is the Z position. If you can define all these parameters, then you can imagine you can combine all the molecules together computationally and generating a 3D structure. So that's the whole idea. And then a lot of computation game is to basically how to determine all these parameters as accurate as possible, because this is related to your resolution. Now, putting this thing into a perspective that is easy to follow, so this is a typical electron micrograph that from Archaea 20S proteasome, and my lab used to work on this one for a long time. Now, this one you can see the individual particles, you can look at them. Then you take many, many thousands of these images, right? And then in each one, then you go in there, either manually, we used to do this manual, now you use computation to identify these individual particles, and you identify hundreds of thousands or even millions of them, and then individual particles. Then you computationally align them together, and then combine them together, generating a 3-dimensional structure. And then after iterative refinement, then you improve the resolution. Now, this was the structure of archaea 20S proteasome, about 5 to 6 angstrom resolution. And this was around the best resolution around 2005. And at this resolution, you can see all the secondary structure feature, and alpha helices, beta sheets, loops. But at this resolution, it's insufficient to detect the side chain. Therefore, we need the atomic structure to interpret in this density map. If we don't have the structure, then we cannot build atomic resolution, atomic structure de novo from this kind of density map. And obviously, to do that, you need a higher resolution. And then the question is, what is the limiting the resolution by this kind of approach? The limitation is not in the microscope itself. Because for material science, for a long time, we used to see, even when I was a student, see this kind of images. Right? This is a graphene picture, a single electron micrograph of a graphene. Out of this kind of image, you can already resolve atoms. Right? But electron microscope already has its resolution power. But for applied to biologic sample, it's not in this level. One of the major reasons is that because this is inorganic material, so it can sustain a large amount of electron dose. For biologic sample, if you use this amount of dose, the sample will be destroyed right away. So we have to use a much lower electron dose and many other limitations. And all this thing together, a fundamental limitation turned out to be a camera that we use. Because remember, we have to take in thousands of images, and we need a high throughput. And in order to achieve this high throughput, we have to use a digital camera. And when people use a digital camera at the beginning, we typically use a CCD camera. And as you know, the CCD camera can detect a photon, but not an electron. In order for CCD camera to detect the electron, one have to put a scintillator code here. It's called a scintillator. This phosphoscintillator converts an electron signal into a photon, and this photon generating a blob. Right? And then this photon then be detected by the sensor. Now, this from one point event to a blob, this deteriorating your image resolution. And then all the camera can be characterized by something called detective quantum efficiency, DQE. And then for the CCD camera, a typical CCD camera has this green curve of DQE. What this means that at the median resolution level here, you can retain about 10% of signal. 90% of signal are lost. And because of this events. And so it was recognized for a long time that in the field that what we need is a sensor that can direct detect the electrons. And with the development of the CMOS camera and the new sensor came along, around 2000, this is the image from recorded with the CCD camera, typical one. This is again 20th proteasome. And then this is a Fourier transform of this image. And you can see this kind of ring goes to about 8 angstrom. Now this ring is equivalent for crystallographer, is equivalent for your diffraction in the crystal. And you want this diffraction go as high as possible. So what we want is that we want this ring go as high as possible. For a CCD camera, a typical one of the best images that we can see, the ring goes around 8 angstrom resolution. That was the limiting. Now with the around 2010, 11, a new generation of camera became commercially available. That is called a direct electron detection camera. Now this became commercially available. Now this one, we get rid of all the scintillator, and then this point spread function was dramatically reduced. And then from here, what happened is that your DQE became significantly improved to this blue curve. And then you can see that this is much better. But this is still not enough, we feel like. And at the UCSF, around 2008, 9, and 2010, we formed a collaboration with Lawrence Berkeley National Lab and a company in the East Bay. And this work is really actually led and pioneered by David Agar, my colleague in our department. So the idea is that because now using CMOS camera has a very high frame rate, the idea is to borrow the same concept from the STORM, super resolution light microscopy, STORM or PALM. And then the idea is that if you have a very high frame rate, in each frame, the electron events are very sparse, they're separated. And if you can identify individual events, then you can actually centroid in where this event, also the charge distribution is distributed over several pixels, but you can actually, from the distribution, identify exactly where these events happen, even to the level of a quarter of pixel. This is called a single electron counting. In this way, you can imagine that your Poynter square function was reduced to a single pixel. That's not the most important thing. The most important thing is that in this way, once you identify the events, you can convert them to a true signal, a digital signal, that without any readout noise, and all kinds of noise is removed. So this became a kind of what we call a noise-free image. And so the idea has been there for a long time, but many people in the field believe that this won't work because the reason is that the camera frame rate is not high enough. And David was the one that really believed that this was really going to work. So he pushed very hard, and Gaten finally accepted this idea, and it was the only manufacturer actually around that time pursuing this idea to develop a single electron counting camera. And when it's finally finished and it became available to us, that our first test shows that this camera performs extremely well, much better than you can see the DQE is significantly improved than without counting. This was a big deal. And because once we have the first version of this camera, when we immediately apply to our same sample, as I showed you earlier, you can see that this tone ring goes all the way to 3 angstrom. When we first see this kind of image, you can imagine the excitement that we have. That means that the image quality now reached to atomic resolution level. And for the first time, it will be possible to actually get into atomic resolution structure directly from this kind of image. However, this is not the only thing. And the reason that many people think that single electron counting is not going to work is because we have the frame rate of a camera, the maximum reached is about 400 frames per second. At 400 frames per second, in order to take an image, we need about a 5 to 10 second exposure time. You can imagine your samples cannot be very steady there during this exposure time. So in a way that is similar, like you take a photographic picture of a bird flying across the sky, that all you see is a blurry feature. And this was indeed what happened. So when this is what we call a perfect image, like the one I showed you earlier, that if we do a Fourier transform, we get this beautiful tone ring to 3 angstrom. However, this type of image, you get about, you take 100 images, you get about a handful at the best scenario that has this kind of quality. Most of the image looks like this. By eye, it looks quite okay, but if you do a Fourier transform, you can see a severe cutoff here. Now, this is because of all kinds of image-induced motion, including that the sample has a global motion and also a beam-induced motion. All this can cause the blurring. The way to overcome this one is to take a movie. This is like everybody, even nowadays, iPhone can do that. You take a movie, then in each frame, the object is steady. Now, this is what we did. But the problem here is that because we're limited by signal-noise ratio, when you take a movie, each frame, the signal-noise ratio is very poor. From here, this is over 25 frames, that you don't see anything. The signal-noise ratio is so poor. And then at that time, a postdoc, Xuemin Li in the lab, came up with an idea how to track all these movie frames. Then they can track them and computationally, so therefore we can track how every frame moved relative to another one. Once we're able to track this one, then we can computationally restore them and move them back. And this is corrected movie, and this is before the correction. And you can see that after the correction, all the information is completely restored. So this is the same micrograph, and this before and after the motion correction. Now with this one, that almost every single micrograph nowadays we took has this kind of quality. So this is a huge deal. Now that means that our efficiency is dramatically improved. And with this one, that Xuemin was immediately able to, this is he's now a professor at Tsinghua University. And then with this one, that Xuemin was first able to demonstrate that with the 20th proteasome, that we were able to get in the structure of about 3.3 angstrom resolution. This is an EM density map. This is X-ray crystallography density map. This structure has been determined almost like in 1997. So as for us, this is a control experiment showing that if we can get this level of density map, we should be able to build a model de novo. So this was a tremendous excitement. However, Xuemin, that time when we had this method to corrective motion correction also is being used, and this paper has been like a most cited paper in Nature Medicine for 2 years, and because everybody used this algorithm. But this algorithm is still not perfect because it only corrects for the global motion. But it turns out that the motion actually has a locality. And around the same time, and short stress at MRC also using working on the ribosome, able to track individual motion of each particle. You can see that the motion in different locations have different motion. So in this way that he can track the locality of each individual particle. But this approach is challenging for small particles because if you cannot see them very well, you cannot do that. So this can only deal with the relatively large particle. But around the same time, that when these two papers published, people tend to, even including us and Schwartz and everybody, basically combine the two together. They use the method from our lab that do the global motion, then followed by this one to do the local motion. And computationally, this is quite expensive. So our idea is thinking that can we combine the two motion collection together to deal with everything in one shot. So the idea following from the actually earlier work from Nico Grigoriev lab, and he's the one actually first characterized the motion using this new type of camera. And he found that he looked at the acquisition virus. He found that a virus particle at the edge of the micrograph always rotating during the beam outwards. So he came up with the idea that the sample actually is not only lateral move, but it actually has a Z motion. And when you have a Z motion in this way, that everything on this edge is sort of rotating outward. This is his hypothesis. And the model is like this way. So we saw that this might be the source of a local motion. The reason is that if you imagine, if everything is perfect going a Z motion like this way, the projection, you don't see that. But in reality, your sample is always tilted a little bit. And this tilting will projecting this Z motion in different locations at different motion. So we test this idea by taking images at a very high tilt specimen. At 60-degree tilt, you can see that motion goes to one direction, almost perpendicular to tilt axis. And if we tilt the specimen to the opposite view, minus 60 degree, the motion goes the opposite direction. Right? It's like this way, you're projecting to go this way. If you tilt the other way, you're projecting to the opposite way. So this kind of proves that indeed the motion is like this way. Now, because this is the way that we think the model, how the motion works, then Sean came up an idea that he divides the entire micrograph into local small patches. And then from these patches, he can get a certain level of locality of the motion. Then he used a polynomial function that to describe the shape as an approximation of this shape of the domain. And then in this way, that from the local motion, he can determine all the parameters here, and then therefore, he can using this formula to correct the motion, local motion at every pixel level. Now, in a way that try to combine the global motion and the local motion all together in one approach that is solving all the problems. And this turned out to working much better than if we do this separately, and at least computation is much better. Now with the same sample that we got 3.3 angstrom resolution, now apply this new method, then the resolution was significantly improved to 2.5 angstrom resolution. Now you can see from now the side chain actually even from the shape, you can actually recognize what this residue is. So this is actually another improvement recently that actually this work now, this method now is also widely being used. So now combining all these things that we can see that what really led to the single particle cryo-EM became much better now than used to be is actually one thing is the direct detection camera as I described to you, that single electron counting improved the sample camera quality, and then also because the high frame rate enabled us to correct for beam-induced motion. This is on the hardware side. But another a major breakthrough in the last few years was also in the software side, because the idea is now using the imaging process, basically not using all the old way, but now including this maximum likelihood approach, that one can further enable us to getting high resolution. But most importantly, that as I mentioned you earlier, that our assumption initially is that all the particles, because of purification, are in the same conformation. You can average them together. But the reality is that they are not. So then if you try to average things are different, then you are trying to average an apple with orange,
then you're never able to get a high resolution. Now, what this maximum likelihood really enables us to do is to do a very good classification to separate all this individually. Therefore, it really enables us to get a high resolution. And then this approach is really independent for the development of this one. But it happens really around the same time when this camera, everything became also available. Therefore, the two things come together at the right time, really jump-started this Cryo-EM to a complete different level. So that's why nowadays everybody is trying to use this technique and to enable to do this Cryo-EM. And this is about kind of like a technology side of what I want to share with you. And then next I will share with you that what our work in the biology side. So for my lab, that for a long time I'm interested in working on membrane protein. And around like 2008, 2009, we started forming a collaboration with David Julius' lab at UCSF, working on a channel called TRPV1. And TRPV1 is an excitatory ion channel, basically can be activated by the capsaicin. Capsaicin is the ingredient in the chili pepper that make your mouth feel hot. And that's why when you eat chili, you feel hot in your burning sensation, this pain sensation in your mouth. And then what's unique about this channel is that it can also be activated by the temperature. When temperature reaches 43 degrees C, the channel will be open. So that's why this hot burning sensation is similar as what we call hot, because it's similar like a temperature rising when you're being activated by the channel. Basically, this one activating the pain pathway. And then this channel, different from voltage-gated potassium channel and the other channel, is that this one is called polymorph because it can be activated by many different reagents and then by chemical and toxins and the noxious heat and so on and so forth. So this is actually a very interesting structure. And for my lab, that we also use this one for a lot of methodology development work. And the reason we pick up this channel is that this was a particular, TRP channel is a large ion channel family, second to the potassium channel. However, this is the one unique ion channel family that until that time, there's not a single crystal structure because it's so difficult to crystallize any member of this channel. So there's no structure there. So we thought, okay, we should using single particle EM without using forming crystal. That's maybe, because then it would generate a big impact. That's our initial thought. And around the same time, that actually the EM has already been applied to the TRP channel. So this is TRPV1 around 2008. And you can see that this is TRPV4 and this is TRPA1. This is what we call wasabi receptor. And if you eat wasabi, activating your mouth, and it's because of activating this channel. Now, if you look at all this structure, that they all give you a rough shape, basically a blob, and nothing at a higher resolution. So at that time, the structural biologists call EM people like me blobologists, because all we can give them is a blob. And then so that's not very interesting. They thought, right? You can, just a blob. No matter what you do, you give us a blob. So our mission was really that initially we wanted to bring the blobology to a high resolution. That's our initial thought. And after spending quite around this time, the only actual high resolution structural information about this entire channel family is a domain called anchoring repeat domain. And then this structure, a small section from the TRPV1 was determined by the Rochelle Godet lab. And so our mission was really to bring this blobology to a high resolution. So after a number of years, actually we optimized the biochemistry, EM, and everything, that we finally get a structure of TRPV1 to about a sub-nanometer resolution, started seeing the transmembrane helices. This was a huge excitement for us around that time, because this was the first time for any membrane protein to start seeing transmembrane helices without forming crystal. And we kind of resisted really to publish this one, and because around that time, we also work out in parallel the direct detection camera, the first motion correction, and we already got the 3 angstrom structure of proteasome, as I showed you earlier. So it was the right time and in the right place. Then we combined the two and applied all the new technology to this one, then enable us to immediately get in the structure of the TRPV1 at the atomic resolution, about 3.4 angstrom resolution. You can see the dramatic difference of this image quality from the CCD camera to the first generation of direct detection camera, and with the motion correction. Now, then we enable us to build an atomic model. Now, this was the first
atomic structure of a membrane protein determined by single particle EM, and also first atomic structure of the entire trip channel family. Now this is the one also sparked actually. Some told me that it's kind of like a wake-up call for the crystallographer, because even with the proteasome, crystallographer think, we can crystallize proteasomes. If we can get the same resolution, it's great, but not a big deal. But now trip channel is the one that crystallography has been spent 10 years trying to crystallize in there, 10, 20 years. No one get a crystal, and the EM able to get a structure, and that make crystallographer really took a different look at the EM. And many crystallographer lab nowadays they switched from the Cryo-EM to a single particle EM because of this reason. And now with the further methodology development, I showed you that using the motion code tool that we actually further improve the resolution further. So that means that everything that is still under development, there's still room for improvement. And around that time, one thing that not only that we determine structure, but another thing shocked the crystallographer community was that we actually determine structure in different conformation. Now this is the able structure. And you can see the channel is in a closed conformation, the upper gate and the lower gate. This is ion permeation pathway. And then the two gate, both in a closed conformation. This is single channel recording, and showing the channel is in a closed conformation. Now this is another structure with capsaicin bond. And this is the ingredient making mouse hot. And in the capsaicin bond structure, the lower gate is now open. And then this is single channel recording. Shows the channel is actually mostly in the open conformation, but frequent back and forth in the closed and open conformation. And in this structure conformation, the upper gate is still somehow completely in the closed. This was what we captured in the closed conformation. Meaning that in this specific state, the channel is still in a closed conformation. But a single channel recording shows the channel actually can open, suggests that the lower gate and the upper gate has some kind of allostatic coupling. The opening of the lower gate destabilizes the upper gate and make the upper gate become less stable. And then the third structure we had is a double knot toxin bond. And now the upper gate is completely open. And then the channel, this single channel recording shows the channel is open. Now all these three structures together showing that there are two gates and each can be regulated autonomously. And then the second is that there are different agents and acting on the different location of the channel. And then together they have a combinatory effects. So that's why this channel can actually integrate different signal and generating unique opening for the channel opening. So these are the work that we published a number of years ago. And as I mentioned to you, that this was actually marked the beginning of what we call the revolution. And from then, what we're thinking about what we should do next, what we should do, and then technologically and also biologically. Now, when we look back to the structure of the TRPV1, this is double knot toxin bond structure, and also give us a lot of information. But we found it's disappointing because the resolution is still relatively poor. Particularly if you compare this one, double knot toxin bond one, with able structure, you can see that this one, the resolution is significantly less than this one. Now this is the same sample preparation and done by the same team, and then why this is the case, right? So the reason that we saw this is the case is that because this sample are membrane protein, we purify them by extracting them out of detergent, using the detergent, stripped off all the lipids, and then substitute them in the amphipore, and then did the structure. And most likely that because of the removal of detergent is the major factor to influence this one. The reason we know that is that double knot toxin binding to from early work, double knot toxin binding to the channel requires the presence of the bilayer. Typically, it binds to the bilayer first and then binds to the protein. Now we remove all the lipids, and this compound may be not stable. This is our rationale. And then to overcome this problem, what one really wants to do is to put in the entire channel into the lipid environment. So this is our next goal. To accomplish this one, and then we chose a system called the lipid nanodisc. And this is basically you have a detergent solubilized the membrane protein, adding with this is what we call a membrane scaffolding protein, and then a lipids, and then you use a biobeads to remove the detergent. This whole thing will assemble into this kind of disc, and with a lipid environment, and then with a protein inside. And then this membrane scaffolding protein basically like a rubber band around the flower bundle, right? So that around here and then bundle the whole thing together.
And this system actually has been used in the past for a number of systems. One particular is this ribosome and then also reality receptor. But both don't get to high resolution. The consensus at that time for the field is that this is a good system, but it's not good for EM to get to high resolution because it adds a large chunk of unstructured mass to your molecule. Therefore, you cannot really get to high resolution. And a very talented graduate student, Yuan Gao, and then joined in my lab and Julius' lab, took this challenge, and he reconstituted the TRPV1 into the nanodisc. This is a size exclusion chromatography, shows that we actually had a nice reconstitution. And this is a SDS page gel, shows that it actually, from this peak, you indeed have the channel and then the membrane scaffolding protein. And then he actually, this is Necfustan EM, and he actually reconstituted this one into two different scaffolding protein. And one has a smaller one. You can see this is how it looks like. The other one is a larger. You can see the protein really floating inside this disc. We initially concerned about this one, that it have a too tightly constraint on the transmembrane domain may constrain the conformation change. So therefore, we chose to use this one. Also, this is less favorable for EM because there's a certain heterogeneity. For example, if you compare these two, that this one, the protein is more in the middle of disc. This one is on the edge of disc. Right? This heterogeneity may influence the resolution. Nevertheless, that Yuan took a challenge, and then he actually was able to get a high resolution structure of this one in the nanodisc. You can see that this gray density here is contributed by the lipid nanodisc, basically by entire lipid bilayer. So this one, you can see the proteins is really floating inside a disc of lipids. This marks the head group of the lipids, basically the boundary of the bilayer. And we also visualize a lot of specific bound lipid. So it enables us to visualize specific protein-lipid interaction, which is a very big deal for the membrane protein field. And then also the resolution improved significantly. Some of the density we can now recognize. For example, this one plugged into this voltage sensing domain. And in the past, we don't really know what this. Now we can model this one as a phosphocytocholin. And we actually then Yuan did a number of structure. This is the able structure. We can compare that able structure which in the nanodisc, what he did now, with the amphipole structure we did early and then published in 2013. You can see that we used this is a new sample, and then we used also new technology, but the resolution actually, compared with the amphipole structure, the resolution is actually comparable, same almost. With this double toxin bound one, the resolution is actually significantly improved. This is an antagonist bound one, the resolution is also improved. From this way, that we can actually think that nanodisc by its own does not really improve the resolution. But what happens is that it really providing a more stable environment, sort of to enable you to getting high resolution. But even for this structure, if we do a detailed comparison, we took this one, one of the helices out of this structure to compare. So this is the same helice S1 from nanodisc from amphipole. Now, if we look at the side chain on this side, facing interior side of the protein, then you can see that looks almost identical. But if you look at the side chain facing our side, facing the lipid, and this side facing the amphipole, then you can see the facing lipid side, that the side chain is actually much better preserved. So this shows that if you have a lipid bilayer environment, the protein is probably still in a much better, healthy environment and are able to providing you a better environment for stabilizing the protein. Now, why this channel actually in the amphipole, toxin-bound structure that resolution can improve, can get higher? We can focus on this region. We can see, for example, this specific bound lipids, its head group form an interaction with the channel, but its hydrophobic tail forms interaction with this hydrophobic domain of the toxin. Now, in a way that these lipids enable a tripartite complex formation that stabilizes the whole complex. If we strip away all the lipids, you can imagine that this whole complex became less stable. And that's probably the major reason why we cannot get a high resolution structure early. Now, from this structure, what actually the most interesting exciting part, is that in the vanillate binding pocket, we observe this very well-defined density. This we can model very nicely as a phosphatidyl isotope. And you can model them very confidently with this one. And in the same pocket, when this vanillin compound, this is a resveratrol toxin, this is a very potent agonist binding here, that it will bind in the specific this same pocket. And we can also model this one. The resolution now enables us to model about 3 Dalton small molecule binding in the pocket. And this is actually quite exciting for the pharmaceutical company, because they are thinking now this technique nowadays probably can be used for structure-based drug design. Now, biologically, this actually gave us some very interesting features. So this is the APO structure. We can see that vanillin binding pocket is not empty. They're always occupied with this lipid molecule. When an agonist comes in binding here, a vanillin agonist, it binds to the same pocket. And the binding of this agonist displaces this lipid. And then once this agonist occupies here, induce some local conformation change, particularly move of this S5 helices, and which coupled by the S6 helices open the lower gate. And so this is actually quite exciting. And then, so the reason that if we look at the also antagonist structure binding here, that it also displaces this lipid molecule, but then stabilize still keep the whole conformation in a close conformation. Now here, these two structures raise an interesting question that we don't have a structure with this empty, completely empty. So we don't know what happened if this pocket is completely empty. Were this one still in a closed conformation or is in an open conformation? So this is something that we still don't know. And then, but this leads us to make some very interesting hypothesis, which I'm going to share with you here. Now, with vanillin binding here, as I showed you earlier, that the vanillin binding come here, displace this lipid molecule, and leaves the gate open. And the same as double toxin binding, then from channel physiology, we know that double toxin binding also open the channel. And then it binds in the up here that we showed you earlier that it opens up the up gate. But our hypothesis is that this one probably also displays the lower gate and then remove these lipids and leaves the lower gate to open. We never captured this structure yet, but this is still our hypothesis. Now, this leads to us to try to answer one of the most interesting questions of this channel. That is, what is the mechanism of heat activation? And this is still so far from structure, never give us a clue that why this channel can be open at 43 degrees C. So our hypothesis now is that maybe it's because of this lipid molecule. And this lipid molecule stabilizes the channel in a closed conformation. Maybe when the channel reaches to the 43 degrees C or in that range, that the energy, heat energy is sufficient to actually displace this lipid molecule with the heat energy, and that could potentially lead the gate to open. And this is actually a very interesting hypothesis that we're still trying to further validate or prove or disprove it. So this actually summarized the work that I have with the TRPV1, and I will use the remaining few minutes to share with you a new structure that we just did recently, and because it's also related to the nanodisc. Give us some more interesting idea. Now, this is another channel called NUMC. This is a mechanosensing ion channel. The channel was identified by genetic screen of a Drosophila, particularly through this Bristol organ. It's a mechanosensing organ that one can put a probe here to measure the current. And if you move this shaft, then you can detect in the current through here. That's in the normal circumstances. Then through a genetic screening, they identify this NUMC. Once you knock out NUMC, this one loses this capability to sensing the movement. Therefore, the NUMC is identified as a mechanosensing ion channel, which is responsible for detecting such kind of movement. And later on, GenLab actually also identified this NUMC in the Drosophila to responsible for the gentle touch sensation. Now, NUMC is a mechano-ion channel. Actually, the ion channel, there are two types of ion channel. Two types of mechanosensing ion channel. One is being regulated by the membrane tension, stretching of the membrane to open the channel. And a typical example is this piezo. And the other one is called the so-called tethering. And the basic idea is the channel is not regulated by the membrane tension, but tethered by something to the cytoskeleton. And then this tether will be regulating the channel open and close. Now, if we look back to the lump C, and it's a tetrameric ion channel belongs to the triple N family. What is unique about lump C is that it has this kind of very long anchoring repeats, 29 anchoring repeats. And Yinlong's lab showed that this anchoring repeats most likely is anchored on the microtubule. If you delete this anchoring repeats, that it loses capability to interact with this microtubule. And also that it loses capability, the channel loses mechanosensation. Now, what the anchoring repeats looks like, anchoring repeats is actually formed this kind of spiral by its own form, this kind of spiral shape. And then AFM also showed that it can actually sustain certain tension. This structure is actually from Minje's lab. This anchoring repeats channel that as a anchoring repeat as this spiral shape, and this was actually initially one thought this might be the shape of this lump C, but on the other hand, it may or may not be the case, because if we look at the A1 structure, this wasabi receptor structure, which also Julia's lab and my lab, we work together to determine this structure. The anchoring repeats have a kind of rather different shape. So from the structure alone, we cannot really, sequence alone, we don't really know what it is on this kind of shape or this kind of shape. So therefore, we try to understand this mechanism. Now, early on, actually, anchoring repeats was proposed to play a major role that formed this kind of bundle in an early model to anchor on the microtubule, therefore to regulate the channel. So our goal is trying to actually determine the structure and really to understand how this works like. And so this was also is in collaboration with the Yinlong Jian lab at UCSF. This is a postdoc, Penjun from his lab, and with David Buckley from my lab, and working on this this channel. So we start this work actually soon after we have the first structure of TRPV1. And then after a number of years, we're actually stuck in a low resolution. You can see this 2D class average, this transmembrane domain, this soluble domain. Some of this 2D class average shows that the particle actually quite well organized. This is most likely contributed by the anchoring repeats. But others are very disordered. So we stuck here for a number of years until we work out the TRPV1 in the nanodisc. Then we change this one into nanodisc. You can see that to our surprise, that not only the transmembrane domain we can see embedded in nanodisc, but this embedded into the nanodisc also make a whole soluble domain became much better organized. We still don't understand why this is the case, but this is enable us to very quickly determine the structure of the lump C in a higher resolution. Without the nanodisc, we are able to get into about a 4.5 angstrom resolution. Not bad, but it's not enough to build a de novo atomic model. But with the nanodisc, the resolution also is just 1 angstrom improvement, enable us to build an entire atomic model. Now, this structure is actually fascinating shape with these long anchoring repeats. And when we first present this structure, people told me that this protein looks very strange, has an evil looking. And the reason they think it's very evil looking is probably remind them of all these movies, of this kind of very evil machinery. And but anyway, so this is the structure. And you can see this long anchoring repeats has this almost like it's spanning almost 200 angstrom. And with a lot of features that I don't have time to go into the detail. But what really interesting is that these anchoring repeats are bundled together through this kind of polar interaction in these two regions. And the polar interaction is not a very specific. Therefore, give these anchoring repeats certain level of flexibility. And indeed, as I mentioned to you earlier, that classification now is a big deal. And then in this whole data set, we were able to, out of the same data set, classify them into 3 different conformations. Now, these are the morphing movie between all these 3 different states. We don't know which one is which, and then what is it. But if we just look at all of them, you can see that all these anchoring repeats has certain motion. But all this motion is insufficient. We can also detect how this motion change this linker domain and kind of leave to some motion in the channel region. But all of them is insufficient to actually open the channel, suggesting that to really open the channel, the motion through this anchoring repeat must be much more significant than this one. And so we don't, but anyway, the kind of our model is that this is the channel with this long anchoring repeats, 4 anchoring repeats bundled together, and then this end anchors on the microtubule. And when the microtubule moves, then this channel will transduce the force or the movement from here to the channel to lead the channel to open. And then the reason you can imagine that you have 4 of them bundled together. Just imagine that a matrix, right? And when you sleep on it, if you have only single spiral, this thing is never going to be stable. It can detect a force in this way, but it's not going to be stable. But if you have 4 of them bundled together, it could generate actually a quite stable structure, not only detecting the force in this way, but also in the laterally. So this is probably one of the reasons. And then we really need that these 4 things bundled together. Now we are starting to engage doing some molecular dynamic simulation, try to further understand whether this kind of motion, how does it detect the motion in all directions, and how does this motion be transduced to open the channel. And we're actually also able to see that this channel can be decorated on the microtubule. So anyway, this is the work that I want to share with you today. And the idea is to show you that a single particle cryo-EM really reached to a level that can work on many different structures. For us, of course, we are interested in membrane protein, and we're also interested in particularly membrane protein in the lipid bilayer environment. And we think now that the transmembrane, this lipid nanodisc, it's a good platform and for studying membrane protein in the bilayer environment. But however, this is not the end of the technology development. There's still a lot of room to improve. We want to improve further the resolution. We want to improve the throughput so that we don't need to take a month to determine a structure. We can get structure in a day or even within a few hours, like crystallography is already doing. Right? We also want to study the things further going to smaller and smaller. For membrane protein, one of the ideas, for example, we want to study for things like a GPCR, which has almost no transmembrane domain, but everything embedded in the membrane. Can we still use in the nanodisc to study things like that? So the field is still growing and rather rapidly. And so we think that really the benefit or the revolution brought by cryo-EM or single particle environment right now is still at an early stage. So you will start to continue to see the more and more excitement from what the cryo-EM can bring to the field. And finally, I want to acknowledge people in the work. These are my current lab member, and these are the past member. Actually, most of the work was done. I mentioned to you, Xuemin is now a faculty at Tsinghua University. He did his motion correction. Mao Fu is did the TRPV1 structure. He's now a faculty at Harvard Medical School. And Champagne did what also a number of other membrane protein. He's now running the cryo-EM facility at Yale. And so all technology work is in collaboration with David Agar lab in the same department. All the TRPV1 and TRP channel work, most of it is working with David Julius lab, also UCSF. The NUMC work is with Yunong Jian lab. So all my major collaboration is actually also within the same campus. This is I feel like very lucky in a wonderful place. And these are the funding agency supported work. Actually, out of this one, that is NSF grant, this one, particularly was the funded for the K2 development and the camera development. And this was actually a grant out of this Obama's economy stimulus pact when he took the office. And we found that this was really one of the money very well spent. We feel very proud of that. And finally, thank you for your attention.
Yeah, a very fascinating talk. A very quick question about the inquiry piece about the TRPV channel. So any idea if that's also responsible to the mechanical force sensing or functionally involved in the temperature sensing?
V1 don't have a, there are some studies show that V1 may have some mechanosensing. Some people say that, but it's not quite clear. But V1, if there is any mechanosensing, most likely it's actually coming from the membrane tension. Because there the anchoring repeats is not anchored on anything, as far as I know. So anchoring repeats is only very short. It contains 6 anchoring repeats in the TRPV. And what's exactly the function of this anchoring repeat is not quite clear. At least it's really one of the things that it's mediating the the interaction between the neighboring subunit. So if you, it's not entirely for the tetramerization, but some says that it may involve the temperature sensing, but we haven't found anything there actually related to the temperature sensing. And it also related to phosphorylation, and some of this part is in ankyrin repeats. Ankyrin repeats actually also have able to bind nucleotide. But what is the function there is also not quite clear. So in this structure, that in the TRPV1 structure, or TRPV, we can, in V1, we only observed the 4 ankyrin repeats. The first 2 was always missing. But in other V, like V2 and V6, and then all 6 ankyrin repeats are there. So far we don't find any other function. Yeah.
Yeah, the hypothesis for TRPV temperature sensing is so far is for the lipid motion will change at a different temperature.
Yes.
How to test that?
Very interesting question. We are trying to think about many different ways to testing it. So one idea is that can one actually generating for example, I can think about widely is that if we can, we're trying to, now our reconstitution is reconstituting in a soybean lipids. Soybean lipids is a mixture, so it contains all kinds of lipids. So then therefore, if you can heat it and cool down, you don't really know what goes out and what's come back in. And so one idea is that can one actually first heat it up, and then not in the lipid environment, and then reconstituting them into a defined lipids without PIP molecule, then to see if this pocket became empty or became occupied by some others. And so that's one way structurally. But the other is that to see if we can introduce mutation, that we can loosen or enhance the binding for this specific PIP molecule. And then to see if that mutation can shift in the temperature. So that's another idea. So that's a number of things that we're working on, but actually many others are also working on it. And even including the using molecular dynamic simulation to see whether this one, because lipids typically binding is very tight. It's very hard to imagine lipids actually can come out of a binding pocket. But this particular one can definitely be replaced by agonist or antagonist. Therefore, we know that it can leave that pocket. So therefore, maybe there's a way to detecting that. So.
Thank you. So you were talking about this for the same protein, they may have different configurations.
Yeah.
But I thought by averaging the same protein with the different configurations, then you average out, you spin out the
your
structure.
resolution also
So
deteriorates.
I just wonder, when you're talking about these ion channels with open state and closed state, if a protein has a few more configurations, how can you recognize it in the structure way? I'm assuming you were referring some patch clam experiment or something, and then so I just did get lost there. How do you uniquely determine by structure?
So there are structure determination wise, that a single particle EM is actually fundamentally is identical with crystallography. So everything, if we want to reach high resolution, we can only average in same type of protein. If we don't average the same type, we lose resolution. Therefore, there are two potential ways to accomplish this goal. One is through biochemically. You purify the protein, try to trap them in a specific conformation. This is what we did in the TRPV1 structure, right? So we know that this channel without any ligand is in a closed conformation. Therefore, we can average all the particles. Of course, we also do sorting on this thing. Then we induce gating by using ligand. And the ligand, then we can know that most particles can be trapped in certain conformation. Now, the other way is that if you cannot manipulate this biochemically, then you can rely on computationally. Then using the computation sorting. Nowadays, we have a much more sophisticated classification algorithm and can sort out many different conformations. And then, so for ion channel to look at the channel pore is still very challenging because it's very small. But for large machinery, for example, spliceosome, like Yigong's lab, what they do is they simply just pour down the spliceosome out of the cell with all kinds of different conformation. They entirely rely on computation sorting to identify individual conformation or states. And then because the conformation change is rather large, therefore they can do that. But with so of course you can imagine, the more subtle conformation change, the harder to separate them computationally. So then we basically taking the both approach, whichever works, either computationally or biochemically. The idea is that by the end of the day, you need a subset of your data which is very homogeneous in conformation. Therefore, you can produce a high-resolution structure.
So there's some guesswork there.
It's not a guesswork. It's really that a very quite. We mostly using a maximum likelihood-based algorithm that you can actually sort out the different conformation, even some of things you've never seen before. For example, the last example I showed you, this is out of same data set. And then we can sort out 3 different conformations that with very subtle conformation change. I actually showed you here, it looks very dramatic. But all this motion is less than about 2 angstrom level. So it's very subtle conformation. We can sort them out.
My question is, the thermal fluctuations. Even for the same solution, you have different configuration simultaneously.
Yeah.
And then
Yeah.
you are out of luck unless you can really resolve it first, and then you can separate them. Am I right?
Yes and no. Yes and no. The reason is that if we are not truly, so when we freeze the sample, we freeze them in all different conformation, right? So you try to identify the one which give you the, so for example, in the NUMP-C structure, you can see that in the transmembrane domain, we reach about almost like a 3 angstrom or 2.9 angstrom. That means in that resolution range, so I don't have any thermal fluctuation or whatever, because otherwise I cannot get a 3 angstrom resolution, right? But in the lower part, the resolution became worse and worse. The bottom part, I could not really, actually the resolution is only about 4 to 5 angstrom, right? And then because that portion has more thermal fluctuation, then I can only reach to about 4 angstrom resolution. The reason is that everything is at the 4 angstrom resolution range, they are identical. But if you want to go to 3 angstrom resolution, they are different. Therefore, I cannot, unless I can successfully separate them. In theory, if you have enough computation power, enough particle, you can always identify a subset which has the same conformation. But in practical, this is very difficult to do, right? But it's getting there, more and more there, you know.
You have to add a southern picture to identify the structure.
Oh, yes.
And then you have to assume the southern picture is same.
Oh, yeah, they are same.
But if they are not the same, then you never...
No, they are the same, then you can separate them.
Yeah.
Right?
I'm saying you have to average out, then you separate them. Without averaging, you cannot separate because you
Oh, you can get believe me, the conformation is very sophisticated actually now, that because what we normally do is that you get a consensus structure, and then you try to sort out all different regions, and you can get a very... Yeah.
That's what I mean, is you need some guesswork. You do this self-consistent checking and do something.
Guesswork is not a good justification, put this way. Yeah, so...
Hi, thank you for the really fantastic talk. I wonder if you could elaborate a little bit more on the technological challenges that you face ahead. Like, which are the biggest pain points? And I guess as an engineer, what are some of the ways that we can sort of contribute?
A very good point. So many people have different idea about what to improve. So for my lab, so we are interested in further improved resolution. So nowadays, it's very common, actually almost routinely achievable to the resolution between 2.5 to 3 angstrom level. Depends on the protein, of course. But getting anything beyond that to about 2 angstrom level is still very challenging. Has a very, there are still some fundamental bottleneck there, particularly related to how we image in the sample. One thing, for example, you can tell is that we can detect in orientation. We can detect the XY position, but it's very difficult to detect the Z position because you're looking at projection, right? But what Z changes is related to your focus. So this is actually still a very challenging question that we don't know what is the best solution. People have been working on it. Without answering this question, that it's difficult to routinely achieve the two-answering resolution. But many people come up with different ways to do that. Now, this is one area we think that the other area is that the throughput. Right now, the throughput, engineering-wise, the throughput is very still, so we need thousands of images. Nowadays, taking 1,000 images take about 2 days, continuous about 24 to 48 hours, on the fly, everything on the fly processing. And computation-wise, you can think about it, we can just, if one can enlarge it, now people using GPU and all this sort of thing, that is still handleable. And then if one want to reduce that one, you need a much better camera, a bigger one. And so nowadays, for example, camera, what we used to be 4K, 4,000 by 4,000 pixel. The new one came out is almost like 7,000. It's about 4 times bigger. But 4 times bigger is not only just the camera, but also everything to handling all this data still needs to be also improved similarly. And so the idea in the future, what we really want is that we want to able to get structure, for example, in a day. And if you from the sample prep to that. Now, another area of improvement is that the sample. And as we are still doing is that we still use purified protein sample. And we also for EM, now even current technology, we use very little sample. And out of 1 EM grids, if everything work out, you use 2 microliter of sample with the 1 mg per mil, this kind of concentration, probably you use 1 microgram of protein. And so it's a very small amount of proteins already enable us to do that compared with crystallography. However, there's currently no way of purifying that such small amount. So if one can miniaturize the protein purification part and then really using that something, a completely novel technology to purify the very small quantity of protein to high purity, that's also a big deal. And imagine that one, then you can really come up with tiny small amount of source and getting the protein out of there. For example, you can imagine that using a tissue sample, for example, from patient. Now you can probably even do that if you can purify that. And another thing that people now, so the technique I showed you, the plunge freezing, this technique has been there for 40 years. We're still using that. We use 2 microliter of sample, but by the end, our protein we actually used is in the picoliter level. Most of the sample we disposed. Now there are people developing the technique that are using almost like a picoliter sample. For example, they use inkjet spray technique instead of applying by droplet or other better freezing. So the plunge freezing we are doing now can freeze about maximum is about 100 degrees C per second. And for trip channel, for example, this is not fast enough. This one means that your freezing time frame is about a millisecond. And can one improve this one to better than say to microsecond? We don't know how to do that. If one can do that, means that your time resolution can be shortened from millisecond level to microsecond level. So this is another, there are actually a lot of, even in the computation side. So we're dealing with very noisy image. And can one actually, using other technique to improve the resolution and the classification, just like you said, that if we can deal with that. Of course, another frontier for the EM, which I did not talk at all here, is the electron tomography. Basically, you don't really need to purify, just look at the whole cell. Can one recognize the cell, what actually all this machinery inside the cell, what they're doing? That's another big deal. So that's another frontier, I think, that in the next, I can imagine that in 5 years' time, the single particle EM will become a complete routine. And what's really challenging and what is really exciting is the cellular tomography. That will bring the cell biology to a completely different level. So that's another thing that I think. That's also at least my thinking. Yeah.
Maybe still, oh yeah.
Okay, thank you very much for the nice talk. Now, one of the future direction is you want to see the smaller particles,
Yes.
right? How far can you go? At this stage, the smaller and the smaller, can other techniques comes in to help to improve the resolution and so on?
Asymmetrical particle as well?
What?
Asymmetrical.
Oh yes, the smallest one people did so far is a protein 17 kilodalton. And the resolution is about 5 to 6 angstrom, not the atomic resolution. The thing is very hard to do. But for two-fold symmetry, I think hemoglobin, people did. That's about like a 40 kilodalton, right? They can get a 3 angstrom resolution. This was just recently published. The idea is that using the phase plate. So the reason is that our imaging right now is that we need to defocus, because there's something I didn't go into detail, like contrast transfer function is a sign function that we have to defocus to generate the contrast. And then the new technology using so-called phase plates to introduce 90-degree phase shift that converted from sine function to cosine function, then you're generating an enormous phase. You can detect a very small particle. And then for that one, that use this technology, then visualize, like I say, 50 kD protein, and then a 50 kD protein can get to about 3 angstrom resolution. That's not a problem. So size-wise, we typically don't consider it a problem. And then, but the related question, for example, if we want to work on things like a GPCR, it's still difficult. The reason is that membrane protein has to embed in a large chunk of unstructured mass. That's the problem. Because it's not only the protein itself, because what we can work on is the structured protein. But if it's included in a large, huge amount of unstructured mass, can one still deal with that one? That's not something that we don't really know what's the limitation yet.
Thank you for your great talk. I just have a small question. So right now, the Cryo-EM will only deal with the protein in the stabilized status, either in the liquid or the bilayer. So I just wonder if some like receptors still kind of shuttle between the cytosol to the membrane. So is there any possible way to track them in intermediate state?
As I mentioned earlier, that you can use, still, the main problem for us is that we still have to go to purification, right? To break cell and purify them. You can use whatever way, tag or something to purify them. And then if there's a ligand or try to generate in some way to trap them in the immediate states, that's possible to get a structure. But there are some of them is still very difficult. For example, if something is voltage dependent, and if you purify a membrane, even you put in the nanodisc, there's no way we can generate voltage across the membrane with an isolated disk. Therefore, we cannot trap them. So the only way to do that is to try to using mutation or other things to mimic that kind of states and try to do that. But really to get to what you're asking is that we hope that in a few years that cellular tomography will enable us to do that. And then there's always a resolution limitation, but the idea is that by say 5 years or 10 years from now, we know almost every protein structure, how it looks like, right? And in current sort of speed, maybe that's actually an achievable goal. And then you can look at these proteins in different conformation states in situ, in cell. So that's at least for us, that is a huge fantasy. It may no longer be fantasy anymore in a few years.
All right. Yeah, in the interest of time, let's thank you, Prof. Cheng, again for